Hello all, welcome back to my YouTube channel all about VLSI. In our previous videos, we have started with the discussion of more counters, where we have seen about the introduction of whatever the counters we are going to discuss, like mod 4 counter, mod 8 counter, mod 16 counter, and the synchronous counters, sub counters, down counters. This and all introduction we have seen in our previous videos, and we have started with the development of mod 4 counter, and we have seen the simulation results of our mod 4 counter also, right? Now, in our previous sessions, actually we have missed one important block in the procedural statements, that is our initial block. Once I will briefly explain about this initial block and then we will move forward. So basically this initial block is also similar to your always block. It is also a procedural block. Now this initial block is a block which is only going to execute once. It is only going to execute once, and it is going to start its execution at time t is equal to 0, and this initial block is non-synthesizable. That is, it can only be used in for your test bench purpose, not for design purpose. Okay, and whatever the statements you are going to write down inside your initial block, those statements are going to execute only for once, and it is not going to execute for multiple number of times, unlike your always block. Okay, and whatever the rules we have discussed in our always block, those rules are applicable for this initial block. Okay, that's it about this initial block. Now, coming to the development of our mod 4 counter, mod 8 counter, and mod 16 counter. In our previous session, we have discussed about mod 4 counter, and we have seen how to develop that and how to write the test bench for that particular mod 4 counter. Now, let us try to write down our mod 8 counter and mod 16 counter. Now, how to write down our mod 8 counter? For writing down your mod 8 counter, we need, for development of your mod 8 counter, we need a 3-bit counter. We need to have a 3-bit counter which is going to count from 000 to 1111. Okay, so this is how we will develop a mod 8 counter. And if we want to develop a mod 16 counter, then it is going to count from, it is a 4-bit counter, and it is going to count from 4 zeros to 4 ones. It is going to count from 4 zeros to 4 ones. Let's say suppose if we have a mod 8 counter like this. How to develop the code for your mod 8 counter? Same which we have developed for your mod 4 counter. How we have developed your mod 4 counter? We have declared a rich, for this mod 8 counter we need to have a 3-bit, let's say, counter, and this we are going to increment for every passage of clock. Counter is equal to non-blocking counter plus 1 tick binary 1. We are going to increment. It is going to count from 000. Next it is going to count to 0001, 010, 011, so on to triple one. And after reaching triple one, it is going to add one more one. Triple one plus 1. What is going to happen? 1 plus 1 is 0, carries 1, and 1 plus 1 is 0, carries 1, and 1 plus 1 is 0, end around carries 1. And since this counter variable is of only 3 bits, it is going to hold this 3 bits, and the last bit will be discarded, and your value will be equal to 000 only. So this is how you are going to develop a mod 8 counter. And mod 16 counter also same. There is no difference. Just declare a 4-bit counter and increment that particular thing, and your mod 16 counter is ready. Okay. Now, let's say if I want to design a circuit. Okay, in the code also we will see once it will be clear. So I will open the mod 4 counter code. This is my mod 4 counter code. Let me open this. This is my mod 4 counter. So what I'm doing for mod 4 counter, I have taken a 2-bit variable and I'm just incrementing so that my mod 4 counter is ready. And if I want a mod 8 counter, I'm going to take a 3-bit variable. And if I want a mod 16 counter, I'm going to take a 4-bit variable. That's it. There is no difference. Now, let's say I have a module with clock, reset, and enable, and my output is a um, and my output is mod 2 underscore counter and mod 4 underscore counter and mod 8 underscore counter. So this is my requirement, and here I'm going to use a signal which is known as mode for selecting all. Okay, let me take one more thing, mod 16 underscore counter. Okay, so I'm going to take something like this, and this mode signal is of 2 bits. If your mode signal is equal to 00, then we should have a mod 2 counter, and if it is equal to 01, it is a mod 4 counter, and if it is 10, then it is a mod 8 counter, and if it is 11, then it should work as a mod 16 counter. We need to design this. Okay, so depending upon your mode, we need to have different type of counting sequences that should be happening. Now how to do this, let us try to understand with one example. So let me create this one more file, create design source. Next, create file, multiple even up counter, and finish. So I've created this file, and press OK and press yes. So multiple even up counter, let us open this file, and let me zoom in a little bit. Now this multiple even counter is going to have your inputs as clock, reset, and enable signal, and one more input as 1 down to 4 combinations, right? So 4 combinations, then we will have 2 bits mode signal, and we will have output rich. So for your mod 2, it is of 2 bits, mod 2 underscore count. Next is output rich. For mod 4 count, we need 2 bits, and for mod 2 count we only need 1 bit, and for mod 4 count we need 2 bits, 1 down to 0, mod 4 underscore count, and output rich. For mod 8 we need 3 bits, 2 down to 0, mod underscore 8 underscore count, and for mod 16 we need 4 bits, output rich, 3 down to 0, mod 16 underscore count. So these are my inputs and outputs for this particular design. Okay, now what should I do? So what I'm going to do is, I'm going to first of all declare a internal counter rich. I'm going to declare it of 4 bits, rich 3 down to 0, counter underscore internal. This is my internal counter which I'm going to declare. Now I'm going to write down first of all the reset logic, always at the rate passage of clock. What I'm going to do is, if I'm going to apply reset, then my counter underscore internal is equal to 0, and let me declare as simply wire so that I can use it in assign statement. Yeah, so counter underscore internal is equal to 0 I've written, and else I'm going to write down in a case statement, case of mode. Now if my mode is equal to 2 tick binary 00, then begin. What I'm going to do is, counter underscore internal of 0 is equal to counter underscore internal of 0 plus 1 tick binary 1, and followed by end. So what we are doing, we are only incrementing the LSB bit of this counter. So let's say if your counter underscore internal, here this is your counter underscore internal, and this is of 4 zeros. Okay, so what are we doing? We are only incrementing this LSB. So what we are doing basically, initially at the first clock edge your values will be equal to 0, next clock edge your values will be equal to 1, next clock edge your value will be equal to 0 0 1 and your value will be equal to 0. Okay, next 0 0 0 1. Okay, this is what it is happening. Or else simply what we can do is we can simply write down counter underscore internal is equal to counter underscore internal, or we can remove entire logic. This is not necessary. Let me show you one more way. Let me declare them as reg only. Yeah, so passage of clock. Okay, let me write down else counter underscore internal is equal to counter underscore internal plus one tick binary 1. So I'm going to increment it. Okay, and followed by always begin and followed by end. Okay, so I'm going to increment my counter underscore internal is equal to counter underscore internal plus 1. I'm going to increment it. It is counter underscore in, yeah. Now within an always another passage of clock, another always block, always iterate passage of clock, what I'm going to write down is case mode. And if my mode is equal to 0 0, then what I'm going to do in this particular case is my mod underscore to underscore count is equal to counter underscore internal of 0. So I'm going to consider my LSB bit. So what is happening here? I will show you. So if my mode is equal to 0 0, then whatever my output is present, that is my mod underscore to underscore count, mod underscore to underscore count will be equal to this counter underscore internal of 0, that is my LSB bit. So only these values will be assigned to my mod underscore to underscore count, and this is mod 2 counting only, right? So 0 followed by 1, next is 0 0 1 0, next is 0 0 1 1. But only the LSB values will be given to your mod underscore to underscore count. So this is what I'm doing. If I consider only my LSB bits, then I'm going to get a mod 2 counting. First of all, let us check whether it is going to work or not. Let me write down end case and followed by end. Okay, and followed by end module. And let me save this. And let us write down the test bench for this. And let us check this one feature first. Then we will go to the next features. Create file, multiple count underscore even underscore tb. Press OK and finish, and press OK here and press yes. So this is my test bench file. So I'm going to declare my reg clock reset enable and reg 1 down to 0 mode signal and wire. So I will copy these things, control C, mode 2 counter and wire 1 down to 0 mod 4 count and wire 2 down to 0 mod 8 count and wire 3 down to 0 mod 4 count, and within semicolons I'm going to write down yes. Now let me declare, I will instantiate this. So multiple underscore even underscore count, let me instantiate them. DUT clock reset enable mod 2 underscore count and mod 4 underscore count and clock reset enable mod 2 underscore count, mod 4 underscore count and mod underscore 16 underscore count. I've instantiated everything, and within an initial begin and block, let me initialize everything. Initial begin clock reset enable mode is equal to 0 and followed by end, and I should generate the clock. Let me generate the clock, always hash 5, and within an initial beginning block, first I will apply my reset signal. Reset is equal to 1. Then I will remove this reset signal. Reset is equal to 0, and then after that, okay, I haven't written the enable logic, so let me write down the enable logic also. Always at the rate passage of clock, else if my enable is equal to 1, then I'm going to start the counting process. So I will write it down here. Enable is equal to 1. Okay, enable is equal to 1, and I will select my mode signal also. Mode is equal to 2 tick binary 0 0. Okay, and after let's say some 70 nanoseconds, 70 cycles, I'm going to make my enable is equal to 0. Okay, and followed by end. So I will write down what happens if my enable is equal to 0 also. Else my counter underscore internal is equal to counter underscore internal. Okay, and let me save this, and let me save this file also, and let us run this. Let me make it as a top, set as top. So we can see our mod2 underscore count. Let me zoom out. So this is our mod2 underscore count. Initially it is 0, next 1 0 1 0 1 0. So this is our mod2 underscore count which we are getting. Now let us write down the logic for our mod4 underscore count. How to write down the logic for our mod4 underscore count? So to take binary 0 1 begin mod4 underscore count is equal to counter underscore internal of 1 down to 0, of 1 down to 0. So why we are taking 1 down to 0? If you carefully observe, I will write down one more time. This is my counter underscore internal. This is my counter underscore internal, and it is of 4 bits. 1 2 3 4. Okay, and if I increment this, it will become 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1, so on. Okay, so if I take only this is my third index, second 1 and 0. If I take only 1 and 0 index, then I can see the count 0 0 0 1 1 0 1 1. Okay, and again it is becoming 0 0 0 1 1 0 1 1. So that's why I'm considering this particular thing, counter underscore internal of 1 down to 0. This is nothing but my mod underscore 4 underscore count, and let me write down end here. Okay, so this is my thing which I have written, and in the test bench let me modify that. So let's say if my mode is equal to 2 tick binary 1 0. Let me save this and run this. I think I have done some instantiation thing, or let me check it. If mode is equal to 0 1 in the test bench, okay, sorry, I have taken the different case 0 1. Let me relaunch it. Yes, so we can see from here in the mod 4 counting, it is initially 0, next we are getting 1, next we are getting 2 3, next 0 1 2 3. So this is nothing but my mod 4 counter. So depending upon my mode signal, I can choose what counting I need, whether I need mod 4 counting or mod 3 counting or mod 2 counting. Sorry, in this particular example we have only mod 2 counting and mod 4 and only even numbers. Okay, now let's say if I want mod 8 counting, so what I'm going to do is to take binary 1 0, I'm going to add that feature. Begin mod 8 underscore count is equal to counter underscore internal of 2 down to 0. Why I'm going to take 2 down to 0? You can see here, if I consider this 3 bits, then I will get mod 8 counting. This is my, if I consider all my 3 bits, then I'm going to get my mod 8 counting. So that's why I'm taking counter underscore internal of 2 down to 0 and followed by end. Okay, let me save this, and in the test bench I haven't instantiated my mod 8 counting. I will instantiate it mod underscore 8 underscore count. Okay, save this. Let us check what we are getting, and we should also change the mode. I'm going to change it as 10. Let me save and run this. Let us check what are we getting here. Yes, so you can see my mod 8 counter is being counting 0 1. You can see here on the left hand side 0 1 2 3 4 5 6 7 and 7 is the last, because 7 cycles only we are making our enable is equal to 0. So if you take, let's say, 100 cycles, then you can see the repetition. Yes, so we can see your counting is get it. So you can see on the left hand side 0 1 2 3 4 5 6 7 0 1 2 and so on. Okay, so this is how we can select our mod 8 counter. And if we want mod 16 counter to be developed, you can simply write to take binary 1 1 begin mod underscore 16 underscore count is equal to counter underscore internal, because counter underscore internal is of 4-bit, right? So we will get the mod 16 counting directly from here. Okay, and let us write down the default case also. Default begin my mod underscore 2 underscore count will be equal to mod underscore 0. Let us write it down 0. And mod underscore 4 underscore count is equal to 0, and mod underscore 8 underscore count is equal to 0, and mod underscore 16 underscore count is also equal to 0. So, and followed by end. This is my code which I have written for selecting multiple counting sequences. So this is how we can develop our multiple counting sequences, and this is simply up counting. Now if we want to down counting, we need to change the little bit logic. Let us see that. So first of all, we have developed our up counting, synchronous up counting. Now, if I want to add some more features like down counting also, how to apply my down counting? I need to first of all increase my mode signal width. So from 2 bits, I'm going to change it to 3 bits so that 8 possible combinations are possible. Okay. So what I'm going to do is, or else we can add one more signal like input up, input up down bar. Like this we can apply one more signal. If your up down bar is equal to 0, okay, we cannot use this hyphen, we should use underscore up underscore down bar. If up underscore down bar is equal to 0, then down counting will be happening. If it is equal to 1, then up counting is going to happen. So up underscore down bar is equal to 0, then down counting is going to happen. And if it is equal to 1, up underscore down bar is equal to 1, then up counting is going to happen. Okay, let us check it. How to do that? Here only we are going to write down else if enable and up underscore down bar. No need to mention equal to 1. If you simply write down as it is going to consider it as 1 only. If these two are true, then up counting is going to happen. And we will write down one more condition. Else if enable and up underscore down bar is equal to 0, you can write it down, or else you can simply write down not of up underscore down bar. Then my counter underscore internal will be counter underscore internal minus 1 tick binary 1. Okay, so depending upon my signals, I'm going to do that. And up underscore it is down bar. And yeah, I've added this, and let me add it in the test bench also. So before enable, I'm going to add this particular thing. Let me check it where I've added before the output after the mode. Here I'm going to add it rich up underscore down bar. Okay, and I will add it here also after my mode signal. up underscore down bar. Okay, and here also I'm going to add it up underscore down bar. Okay, and what I'm going to do here, up underscore down bar. Okay, now here what I'm going to do is, by default it will be in up counting because it is equal to 0, right? Here I'm going to do down counting, up underscore down bar is equal to 1 tick binary 1. I'm going to write this, and mode is equal to 10, that is it is being in the mod 8 counting process. And let me save this, and let me save this file also and relaunch the simulation. Let us check in the output. So what are we getting? Let us check it. Where is this? It is being up counting only. Let us make it as down counting. Sorry, if it is equal to 0, then we are going to perform a down counting, right? Okay, okay. Let me relaunch it. Yeah. So let us check what is the output which we are getting. So initially your value is equal to 0. Then what you're getting, it is 7, 6, 5, 4, 3, 2, 1, 0, 7, 6, 5, and so on. So this is how we can either control up counting or down counting, and we can choose what type of mod counting we can have using a single design. Okay. Yes, so that's all about this particular session. In our next session, we are going to discuss about frequency divisions using these counters, how to write the code for frequency division. And before that, we will discuss how to generate your mod 3 counter, mod 5 counter, mod 7 counter. Then we will start with the discussion of frequency divisions from these counters. Yes. So that's all about this particular video. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.